All right, so I think we should just start with the title. We have Chapter 3 Desk, Footnote 1 Actuator. The footnotes are the parts to the main chapter video, and in this case, we're going to be making an actuator for that desk. In Chapter 2, we made a actuator that was like this long and extended to about there and retracted. I want to take that concept in this video, but scale it up to be like this. Because on that desk, I want to attach these large actuators to do different things on the sides or wherever it's going to be. So let's just get right into the drawing and then the build.
Welcome to this one-way ride. We're all on it. Got to give it a go. All we got is hope. Don't you know? Wipe the floor of yesterday. You can change it anyway. And you're never alone, never alone. Doesn't matter what they say, doesn't really matter what they do. Let go, baby, let me breathe it now. Let go, breathe it now. Doesn't matter where I go, heart still open, cannot close. Let go, baby, let me breathe it now. Let go, breathe it now. Took my head out of the sand. We're all in it, better. Open your eyes, see the open sky. Don't you know? Shake whatever brings you down.
A few quick things before we talk about some specifics. There's a 4-pin connector on the bottom, and there is a 2-pin connector on the top. For the bottom, those 4 pins are ultimately for controlling the motor. 2 of the pins are PWM pins for changing the speed and the direction of the motor. The other 2 pins are just for providing power to the circuitry in order to have enough power to power the motor. So I was so excited the other day that I said, oh, look at this thing, and then I dropped it, and that was disappointing. But breaking isn't always bad because it shows you where something is going to fail, because eventually it will fail in some way. So this was the piece, kind of goes on like that, and it came down and it broke in that way when it hit the ground. And it just snapped off like, obviously the weakest parts. I have this kind of channel on the inside just to reduce material or pass wires. I can either make that smaller, or I can make the overall piece larger to increase the strength. To measure the distance between the top of this and this, you want to hold a certain position. So say that's 20 inches, and if it goes too far up, this thing has to retract. If it goes too far down, it has to extend. The device to take that measurement that I'm going to use is called an ultrasonic distance sensor, which is just a sound wave sensor. And what it does is it sends a sound wave out of one of these eyes. It hits some surface, and then it comes back and it gets received in the other eye. The sound wave itself will travel at 343 meters per second. And knowing the speed of sound as well as the timed interval between sending out and then receiving, you can back calculate what the distance is to a particular object in real time. So that's what I'm going to do. So we've completed the wiring of this. A number of things we got to talk about. The first will be this cable tray. So in the cable tray, it takes the cables from the top, brings it through this roller coaster like loop and out this black cable. But also cables from the bottom are routed up the side and also in this black cable. Something though that I had a lot of trouble with was these two black pieces. Starting in the back, this was just used for alignment, but you can see that regardless, the teeth in the front were just catching. This piece of paper, when I slip it in, it completely fixed the problem. There was no more catching, and it fixed it so much that I 3D printed another piece to have that kind of mimicking paper lip with a slight fillet at the end to make sure the teeth never catched. From here on out, there were no issues, so I moved on to the next part. The next thing that I want to talk about is the motor. So you can see there's two motors here, but previously, I think I showed one motor. The plan was always to try one, see how well it does, and probably upgrade to the two. And I did just that. This worked, but it wasn't quite like satisfactory. With the two, they're working together. I'm able to get the speed and power that I need for my particular application. Another thing to talk about is this upper piece. So there's two things on here. Let's see if I can show the camera. There is the distance sensor and then this kind of ledge piece. The reason for the ledge piece is this is going to be mounted vertically just like this, and I want to be able to mount things to it. And I'm not talking about like really heavy things. It's just, maybe I'm going to attach a light, or maybe I'm going to attach, little alligator clip arms to hold the circuit board. So now that all of this is done and we have an exit cable, that black cable that goes out, we have connectors on the end of it. We're going to work on the circuit board that this will plug into. And then after that, do programming, and finally getting to a stage that I'm really excited about is a demonstration of this, being a certain distance from the ceiling or whatever it might be. So let's get on with it.
Things got so complicated, not like it was before. At the edge, we should break it. You keep on coming back for more. I've been waiting here before. It is not the first time, thinking that you'll come around. I've been waiting here before. It is not the first time, thinking that you'll change this time. No, I don't need a heartbreak. I don't need to save you, 'cause I gotta be you, 'cause I gotta be you. No, I don't need a heartbreak. I don't need to change you, 'cause I gotta be you.
Okay, so what I want to do next is run through a number of demos, but just before that, I want to talk a little bit about the actual control system associated with this. So that includes things like the PID controller, set point, the feedback, the error associated with all of that, PID constants, all of those concepts that I really struggled with for a really long time, and I thought somebody out there might find it useful as they're trying to figure this stuff out too. If that is not your thing, just skip ahead to the actual demos and stuff. But if it is, that's what we're going to do over there. Okay, so the first thing that I want to start off with is what is on the screen. This red line is something called a set point, and this blue line up here is something called feedback. The set point is a desired location that we want to go to. So the computer in this case is just outputting a value of 0, and that is where we want to go. The blue line up here is where the system actually is. So it says 99 right now, but that's just because the system is off and it's spitting out a random value. But later, you're going to see that this value is actually what is being detected by this system. So as it goes up and as it goes down, in real time, what it's actually reading is this blue line. Before we actually turn it on and give power to these motors to move, I want to talk more about this red line. So right now the computer is just saying go to a value of 0. But I would like to talk about a sine wave, because I would like this thing to, have an oscillation in its movement. So a sine wave by default is just a value multiplied by 1. And this thing is by definition then only going to move up and down a tiny little bit. If I were to increase this to 10, you'd see a larger oscillation. So let's start with that, changing it to a value of 10. Okay, so you see changes in the set point value. So the computer is saying, I would like you to go down to a value of 10 and then up to a value of 10 and go back and forth just like that. That said, you can see that the blue line, nothing's actually changing in real life, but it makes sense because this is not powered. The motor is not on, so there is going to be no movement. But we're still telling it from a set point standpoint, you should move to -10 to +10 and like that. Before we actually do the demo, we need to tweak what the set point is going to be a bit more. The first thing to tweak is we want to increase the range of movement. So by increasing this to 80, you're going to see very similar motion, but instead of going from -10 to +10, we're now going from -80 up to the +80. And this allows us to utilize a wider range of this actuator's motion. But let's take another piece of information here and let's try to visualize what is actually happening. That is like saying if this is the 0 location and this is the actuator's maximum position of 100, the actuator can go from its 0 position, let's try to increase this a little bit, it's going from this 0 position up to a maximum of 100. That is what the actuator can do. But we are saying go from 0 down to -80 and then go up to +80. So that is saying go up to 80, 0 to 80, but then have this physical point go to -80, which is never going to happen because this thing would have to literally go into the floor and it would completely break, right? Obviously, it can't do that. It has a limit. This top piece can only go to where this 0 position is, or the top piece can go to 100. So we can't work with these negative values. In order to get around that, you can take the absolute value of something. And what that just means when it comes to a sine wave is only use the positive values here. And every time you go negative, instead, just do another positive bump. Like that, like a bouncy ball almost. So let's go ahead and upload a program that has this inside of it. All right, so we're going upwards from 0 up to 80, but now when it hits this, it goes bloop, like a bouncy ball, and it's just gonna have this kind of bouncy ball effect, but with no loss of energy. So it's just gonna infinitely bounce like that forever. So that takes care of this negative value. And now we're just bouncing from 0 to 80. Okay, but here's yet another thing to think about when you're doing this. If this top black piece were to go all the way to this top surface, on the inside this pink piece obviously then would have to go, this distance, which it's right here right now, it would go all the way to the end. It would bottom out at the bottom of this black 3D printed piece, which means it's going to crash into the wall. So you don't really want to go all the way to, you don't want this piece to go all the way to here. Maybe have it go to 10 or something. So have the black piece go to here. But the same problem is going to happen when you go to the top as well. So you also don't want it to hit the ceiling, and that's where you have, that's why we're not going all the way to 100. So let's add this offset. That's what this equation just does. We're creating an offset of 10. Let's upload that program. And we're gonna see it's gonna start at 10 now. So about right here, it's gonna start, or there. And instead of going to 80, it's now going to 90, because let's just say 90 is right here. Let's say 90 is here, just for the sake of it. It's now going to go from 10 to 90 because this is a shift of the entire red wave. And you can see that. It's this shifted up by 10, which means the top also has to shift by 10. But that was also part of my plan. I wanted it to get to lowest it would get to is 10, and the highest it would get to is 90. So let's review just a little bit before we actually turn the motors on. We have the red, which is the set point. We have the blue, which is the feedback, which once we power the motors, very quickly we're going to see this blue line try to get as close as it can and follow and track this red line as best as it can. And the difference between the two, as you might have seen the preview, is the error. So the error is the difference between the set point value and the blue value, which is the feedback. Let's do this. Let's turn it on and see how this works. Watch it for a little bit. Gets to about 90 and gets to 10, which it looks like 10 is probably about here. Let's see if we can actually line it up for the sake of interest. Oh, 10 is here. 10, and it looks like 90 is, let's see, do we get there? Okay, yeah, so that is the range of that we have set the actuator to go to, but the actual range is from 0 to 100. Let's also do this for the sake of it just looking like a good scale. All right, so now that we have it moving, we have a better understanding of what is going on. We know that we're trying to get to the red. We actually, in real life, are getting to what the blue is reading. We can then, get a bit deeper into the weeds and be like, well, it's pretty good performance, but what if I wanted even better performance? What if I wanted this blue line to get even closer to that red line? I'm going to gloss over this next part, but I still wanted to talk about it. So the controller that is actually running inside of this actuator, inside of the microcontroller, is a PID controller. And let's just power this off for a second to talk. The PID controller has 3 variables in it that you can tweak. You have a KP value, you have a KI value, and you have a KD value. The values for the controller are actually not looking at specifically the red line or specifically the blue line. They're looking at the difference between the two. And I mentioned previously that is what the error is. It's the difference between the red line and the blue line. Let's go ahead and upload a visualization of the difference between the two, which is called the error. Okay, that program's uploaded now. And what we have is exactly what we just talked about. Again, the red line is where we want to go. The blue line is where we actually ended up going. And the green line is the error. It's the difference between the two above lines. That's why you can see in real time, they're kind of along the same axis, because this is the time axis. Okay, I want to take a step back here and think a little bit more about this error and how KP, KI, and KD are using it to help with reducing the error in the control system. So let's start with this green section that is above 0. So just the positive. It goes up like this and actually drops down here, but let's just focus on this one part. So every point on here, let's just say it looks like that. Remember that every point is the set point minus the feedback, which gives you an error, and it tells you how off your system is from where you actually want the system to be. For the sake of simplicity, I'm going to act like instead of there's all of these points, there's one point here and there's one point here, okay? And if you were to just connect the two, it would just be a line. So let's just act like this for now, that this is all we have to work with. Starting with KP, KP is going to be associated with the most recent error point. And in this case, if you were to drop it over here, let's just say that that is 5 and this one is at 10. KP, let's just say it has a value of 2. It's just a constant. You can change it at any point in time, but let's say right now it has a value of 2. The KP's contribution will be whatever its value is times whatever the error value is that has most recently happened. So in this case, it's going to be 5. 2 times 5 is going to give you 10. 10 is going to be the how much KP is going to contribute to making the error reduced to 0 as fast as possible. If you had this as 4, then that would be 20. It's the amount of control effort KP is going to have towards reducing this error. So it's only looking at the most recent point. That said, if you have KI, KI is associated with integration. Let's highlight this and let's show that on this point, on this curve, it's not only looking at the most recent point, it's also looking at the prior point. And it's saying that given that it's integration, what is the area underneath this curve between these points? And that would be this area. So you could do integration, or you could just calculate the area by getting this triangle here and then adding it to this rectangle and getting the total area. And let's just say Ki had a value of 7, just for the sake of it. It's going to use the area with its value of 7 to try to get the controller again to reduce this error as fast as possible. The last one we have is KD. KD is associated with the derivative, and you can think about it very simply as associated with the slope between these 2 points. So if you have a downward facing slope or an upward facing slope or a very aggressive upward slope or whatever it is, let's just say KD had a value of 8. Again, that's a random value. It's going to work in association with the slope to, again, just like the prior two, it's going to work with the slope in order to help the controller reduce the error as fast as possible. And you'll see that the game is trying to adjust to these 3 so that you get the best performance out of your controller to reduce the error associated with your system as fast as possible without creating more problems. And the idea, the game you can play is say, I need to adjust the KP, the KI, and the KD values so that we've reduced the amount of jumping up in error as well as bouncing down in error. We want to get that as close as possible to this 0 error mark, because in real life, wouldn't it be great to just say, if you subtract the 2, you never have any error? Well, you're never going to quite have that because there's always going to be some lag between the blue line and the red line. Because if you didn't have that lag, then it would just mean both things know exactly what both things are doing at all points in time. You know, maybe some future that'll be real, but not today. The values that I actually have in this controller are a KP of 15, a KI of 12, and a KD of 1. That's actually what the controller is using from a gain standpoint. I would like to just show that what if I change this, the proportional gain to like, let's just say 3, something really tiny, and see what happens if I were to change that value. Uploading. Let's watch it for a minute. So you already have a huge issue. The blue line is kind of way out of whack with the red line. And visually you can see the green line, how there's this big difference between the two, both positive and negative. I'm just showing this because you can physically see the difference between these kind of nicer curves and the obviously, you know, bad lining up tracking between the two. You can continue to tweak these things, but I'm just for now going to put this back to what it was and call it quits. The next thing that I would like to do is take a distance sensor, another one, a separate one, and use it to say, when I go up, this thing should also go up with me. If I go down, you should use it to make sure that it also goes down with me. The other thing that I wanted to do is what I started with the beginning on is you take this thing and you should be able to bring it close to the ceiling, and it should always make sure that it is a certain distance away from the ceiling no matter what. So we're going to do both of those demos next.
Get me off of your mind. I was no good, they said. You could do much better, but you gave them one middle finger and the door shut. 'Cause I know we are real as can be. Although we stick to each other, we're free. We still dream of what we could be. You still amaze me. Us lasting longer than them, standing stronger than them, letting think we are crazy. 'Cause I know we are real as can be. You still amaze me. Now that we've come so far, they're going nuts about how happy we are. See the bond that we made. It all seems real now that I'm not afraid. And we really got them. Yeah, we sure did write it out. 'Cause we have each other. That's what it's